Hi dear children, in today's class we are going to study about what is called a displacement method. This is a problem solving method. We will first learn about the method and we will try two problems based on this method as given in the NCERT book. This is very important because we had questions based on displacement method for GMAIN 2020 as well as this Central Board of Secondary Education board examination. So take it seriously and learn it properly. That is my request to all of you. So what I'm saying is that as the name suggests, displacement method, here we have an object here. This is the position of the object which is fixed. This is this position of the screen where we are going to get the final image, that is also fixed. The object is fixed, screen is fixed, but we can move the lens so that there are two different positions of the lens for which a real image is obtained on screen. And we want to find out the corresponding values of the positions U and V of the two lenses. That is our requirement. Let us quickly proceed to our method. Now, as I told you, this distance is U and this is V. So, length U plus V is equal to D. Here I am not taking sign convention. D is the distance between screen and the object, which is a fixed quantity. Which means V is equal to D minus U. Right? So we have the formula for focal length F is equal to UV divided by U plus V. Again, by using sign convention, one can say minus U into D minus U. Okay. Divided by, okay, or rather just we take this as such, U minus V plus V. Minus U, as U is negative. V is positive, it is D plus U, D minus U, divided by minus U minus D minus U. Right? So from here you will get F is equal to, what I am saying, UD minus D square, U square divided by capital D. I request you to make the simplification of this expression. There is a minus here, minus will be cancelled throughout. Or we get dF is equal to UD minus U square. Right? This is a quadratic equation of U, or rearranging this, U square minus UD plus D square is equal to 0. U square minus UD plus D square is equal to 0. Bringing U square to this side. Sorry, it is not D square, it is DF. U square brought to this side, it becomes plus. UD brought to this side becomes minus UD, then DF. Now this is a quadratic equation with the U as the variable. Now the solution of this equation is U is equal to D plus or minus D plus or minus root of D square minus 4DF divided by 2. Now here I use the equation. So if the equation x square plus bx plus c is equal to 0 implies x is equal to minus b plus or minus root of b square minus 4az divided by 2a. So in place of x we have u, in place of b we have minus d. So minus of b becomes plus d, plus or minus b square, that is d minus d the whole square, which is d square, minus 4 into, in place of a we have 1, 4 into 1 into, in place of c we have df. So d square minus 4df divided by 2. Right? Now for real values of u, for real values of u implies I want u is the distance of the object from the lens, which is always going to be a real number, right? It is always going to be a real number. D square minus 4df should be greater than or equal to 0. Right? Greater than or equal to 0, because the term in the square root must be positive. Right? For real values of u, the term in the square root must be positive. Term in the square root must be positive, right? Term in the square root must be positive, which means d square greater than or equal to 4df. That implies d greater than or equal to 4f. Now I'm just wiping off this part. We require it later, but for the moment. So u plus v. So first of all, understand that u plus v is equal to d. That is important. Okay, so from here, d minimum. From here, I am getting d minimum is equal to 4f. So what is d minimum means? It is object and this is screen where I am going to get a real image. Okay. So the most important point we can say is that the minimum separation between an object and its real image for f. The minimum separation between an object and its real image is 4f. So understand that is very important. That is what is given by this expression. This can also be said in another way. Another way we can say the same sentence is, for a fixed object and screen, comma, maximum focal length of the lens, maximum focal length. So here D is fixed and I am placing a different lenses here. And what is the maximum focal length of the lens which can give a real image on the screen? F max is equal to D by 4. In that case, the maximum focal length of the lens which can give a real image on the screen is D by 4. Ready? So these 2 points are very, very important, I tell you. Since the size of the body is very less, I was forced to wipe off what is wrote on the board earlier. Now we'll start from the solution of the quadratic equation. We got u is equal to d plus or minus root of d square minus 4df divided by 2. Which means we have 2 positions for this. One is u1, right? u1 is equal to d plus root of d square minus 4df the whole divided by 2. This is u1, right? Now correspondingly v1 is equal to d minus u1, right? That is what is our knowledge. I just said the value of u1, not taking into consideration of the sign convention. This is the value of u1. So d minus u1. So d minus d by 2 plus root of d square minus 4df, that again divided by 2. What did I do here? I just splitted this into two parts. You know, 1 plus 2 the whole, 1 plus 3 the whole by 2 is equal to 1 by 2 plus 3 by 2. So the same procedure is what I have used in splitting this expression. Now what is, okay, now I will put a bracket here. What is d minus d by 2? It is equal to d by 2. So I am getting v1 is equal to d by 2 plus root of d square minus 4df. Okay, let us, for our convenience, I am going to do one thing. I will put small d is equal to d square minus 4df root of. In that case, I will get this as, this is equal to capital D plus small d by 2. I'm writing small d as this thing, right? So in this case, u1 is equal to plus or minus, I'm sorry. This one is equal to d plus small d divided by 2. Correspondingly, I got v1 is equal to d square minus 4df by 2, which is equal to d plus small d by 2. Agree? So this is the first case I am saying. u1 is equal to d plus this value, that is d plus small d by 2, and v1 is equal to this thing we got. Now the magnification in this case m1 is equal to, the magnification m1 is equal to what? v1 by u1. v1 by u1. In this case, I am just writing the magnification magnitude only. So v1 by u1. Sorry, v1. This will be, I made a mistake. So this is minus here, right? Minus. So d minus small d divided by d plus small d. This you can prove. Dividing this equation by this equation, right? 2 is common at the denominator, so it will cancel. So what kind of image you are going to get here? For this u1, you will get what image? You will get a real image. As already I told you, it's a real image. I don't know if you will be able to see this. It's going to be a real image, real inverted. Real images are generally inverted for a real object, and diminished image. This is going to be a diminished image, right? It's a real image, but it's a virtual image, as well as it's a diminished image as well, right? So this is going to be the image that you are going to get here for this condition. Now second case we will write. Okay, u2. This is u1. Second case, u2 is equal to then what? D minus. Again, I will put D minus here. So v2 is equal to D minus u2. D minus u2. So D minus D by 2 plus this thing. Here also plus. Here also plus. In this magnification, it is plus. This is minus. So what kind of image you are going to get? In this case, you will get the images magnified. Corresponding to this u, that is u2, you are going to get a real image, an inverted image, as well as a magnified image, right? So what you see here is, what was u1 earlier? u1 is equal to d plus, d plus d by 2. Correspondingly, we got v1 is equal to d minus d by 2. We got u2 is equal to d minus d by 2. Correspondingly, v2 is equal to d plus d by 2. So what do you see here? This again proves the principle of reversibility. First u1 is v2. u1 is equal to v2, right? What you see here is u1 is equal to v2 and u2 is equal to v1, right? Question. Now what is u1 plus u2? So all this point we have on our board. Probably you might have noted. Now from here you can see that U1 plus U2 is equal to capital D. Right? And U1 minus U2 is equal to small d. Small d is the, where small d is equal to what we got? D square minus 4df with a root here. Agree. So U1 plus U2, you can add to get this answer. U1 plus U2, this is U2. U1 plus U2, that is d by 2. So when you add, this is plus d, this is minus d, these two will get cancelled. So U1 plus U2 is equal to capital D. U1 minus U2, this capital D will be cancelled, plus D, minus of minus plus, D by 2 minus minus D by 2, it becomes D. Okay, so now let us have this in our figure. As I told you, this is fixed. What is fixed? The object and the screen are fixed. Now this is the first position. Now I will tell you this is U1. And correspondingly this is V1. We got an image on board which will be a magnified image. Oh sorry, U1 is equal to what we wrote? U1 is equal to capital D plus small d divided by 2. Right? So I'm sorry, I have to draw U1 not here. U1, in this case U1 is greater than V1. So this is U1, this is V1, right? Now in the second case we got, again for the same object and the screen, the second position of the lens where we are going to get the same image on the screen is here. This is the position of the lens. Correspondingly this distance is U2. That distance is V2. Yes. Now you can see here. So this separation, this is U1, this much is U1, this much is U2, and you can see that this is equal to U1 minus U2, which is nothing but small d. U1 minus U2, this is equal to small d. That means we can define small d as the difference in lens positions. Difference in lens positions for which a real image is obtained on the screen. The difference in the lens positions for which a real image is obtained on the screen is small d. Screen is small d. What is capital D? Capital D is the distance between object and the screen. Now from this relation, so already we got small d is equal to this thing, right? Now I can say from here focal length f is equal to, I will square this equation, then I will modify. Small d square is equal to capital D square minus 4df, right? So 4df is equal to capital D square minus small d square, right? From here the focal length f is equal to capital D square minus small d square divided by 4 into capital D. So this is the expression for focal length. What is capital D? Capital D is the distance between the source and the screen, or the object and the screen. Small d is the distance between the lens positions. Distance between the lens positions for which a real image is possible on the screen. So let me tell you, this is the aspect I want to say regarding the displacement method. And one more thing we have to say is the magnification M1 is equal to V1 by U1. V1 is equal to U2, I said this is U2 by U1. And magnification M2 is equal to V2 by V1. V2 by U2, that is equal to U1 divided by U2. If you just multiply M1 and M2, you will get the answer is equal to 1. The product of their magnifications in case of a fixed object and screen will be equal to 1. Product of magnifications, as you can see here, V1 is equal to U2, V2 is equal to U1. So the product of their magnifications is always going to be 1. So this also is an important point you have to understand. I hope this discussion of displacement method is clear to you. Now, to understand the concept of displacement method, we will discuss exercise question 9.20 from the NCERT book. Let us quickly read the question. A screen is placed 90 centimeter from an object. The image of the object on the screen is formed by a convex lens at two different locations separated by 20 centimeter. Your question is to determine the focal length of the lens. This is a question for you. Let us see how can we solve this question. Pause the video for a minute and try this by yourself first. Then I will take into consideration the question. Okay. What is the first information? What is 90 centimeter? 90 centimeter. Let us reduce our points into the terms we said. We have to find out focal length. So focal length of the lens, we have the formula capital D square minus small d square divided by 4 into capital D. What is capital D here? What is capital D here? Distance between object and the screen. What is the value of capital D? That is a distance between screen and the object. You can understand just by looking at this part of the question. Screen and object, what's the distance? Between screen and object, what do you see? 90 centimeter. So capital D is equal to 90 centimeter. What is next you require? You are asked to find out focal length of, this is the requirement. Which means now we need small d. What is small d? The distance between the lens positions for which a real image is obtained on the screen. Distance between lens positions for which a real image is possible on the screen. So what is small d is equal to lens difference between the lens positions, real image is different locations separated by. So small d is equal to 20 centimeter. Now let's calculate the focal length easily. What is focal length f going to be here? This is 90 square minus 20 square divided by 4 into capital D, right? That is 90. Let us simplify this. This is 90 plus 20. I use the formula as a square minus b square into 90 minus 20 divided by 4 into 90. 110 into 70 divided by 360. So let us make this cancellation. So 7 by 36. So this I am going for an approximate method. This is 110 divided by 36 by 7 is for around 5.14. So I am just taking it as 5 itself. 36 by 7 is 5 approximately. So 110 divided by 5. So you will get this answer as approximately 22 centimeter. But I would say the answer should be something between 21 and 22. So it will be 21 point something. I hope I am expecting the correct answer that you can calculate by yourself. So this is a simple. This is the so doing by displacement method. This problem becomes very easy. That is the reason for teaching what is called the displacement method. Hope it is clear. See the question. The image of a small electrical bulb fixed on the wall of a room is to be obtained on the opposite wall. So the bulb is here in this wall and I want to get the image on the opposite wall. So this is the object, this is the screen, and the separation is 3 meter. So what is the variable mentioned here as 3 meter? That is capital D, right? Distance between object and the screen is capital D. So capital D is equal to 3 meter, right? What is the maximum possible focal length? So you're asked to find out F maximum. We have direct method of solving this. We can find out F maximum very easily. What is the method of F maximum? F maximum is equal to D square by 4. Right, sorry, D by 4. So D is 3 meter divided by 4. This is 0.75 meter. Unlike the length of the question, the solution has not much length. It's a very simple question, I will tell you. Again, this question is done by means of what is called the displacement method. I hope the problem is clear to you. Different problem for discussion. This is again an important question from NCERT book. This is exercise 9.8 question. And the question says likewise, a beam of light converges at a point P. So this is a converging beam. Right, so this is the point P. What happens then? A lens is placed at a distance of, a lens is placed in the path of the convergent beam at a distance 12 centimeter from the point P. A lens is placed. Now here you see at what point does the beam converge if the lens is a convex lens of focal length 20 centimeter and a concave lens of focal length 20 centimeter. So let us solve this. So let us take the first case where we keep a convex lens. Now these rays, so once I place this rays, I place the lens, I will just make it dotted, because in that case, now these rays will behave like a what? Virtual rays, right? Which appear to converge now. Here, this is this image, the image formed at the point P will act as a virtual object for the refraction. It will act as a virtual object. So I am measuring U in that direction, right? U is measured in the direction of the incident ray, right? So here, as we were taking up to now U as negative, here we cannot take U as negative. So many of you might have thought about the doubt from the previous classes. So while taking the derivation, we have applied sign convention again. While solving the problem, you are again applying sign convention. What is the use of it? That is because for real objects, U is negative. I tell you, for real objects, U is negative. For virtual objects, which will be on the other side of the lens, U is positive. So here I have to take U as positive because in this case I am measuring U in the direction of the incident ray. So I will take this as plus 12 centimeter. U is equal to plus 12 centimeter. I need to find out V. I have the focal length F is equal to given plus 20 centimeter. Alright. We have the formula for V for a lens as UF divided by U plus F. Let's substitute for these values here. So U is equal to 12. 12 into focal length is 20 divided by 32, right? 12 into 20 divided by 32. So what is 12 into 20 divided by 32? Let us solve it. So this is 5, 8. This is again, okay, so 5 into 12, 12 into 5 is equal to 60 divided by 8. 60 by 8 means 30 by 4. 15 by 2, this is equal to 7.5 centimeter. So what you see here is that as a result of keeping this lens, this is a converging lens, so it will form image closer than earlier. So this is the location of the final image as we keep a convex lens in the path of the beam. Now let us take the second case. That is when we place, instead of a convex lens, if I place a concave lens. I think I need to redraw the figure once again. Not complete. I am so lazy to draw figures, as you all know. Now I'm going to place a concave lens. This is a concave lens. And in this case, what is the focal length given? 16 centimeter. As it's a concave lens, it is minus 16. Now this will give you the answer. Yes, let us see how the answer is going to change here. 12 into minus 16 divided by 12 plus minus 16. U is positive, right? So this is 12 into, yes, minus 16 divided by minus 4. So I am getting it as 48 centimeter. You got the answer as 48 centimeters. So what happened here? So this lens has produced a diverging effect. So since I need to incorporate that 48 centimeter, I will make this smaller. This is actual point P is here only. This actual point P. As a result of placing a divergent lens, you're going to get, as this beam will be diverged by this one, so you will be getting that image at a distance of 48 centimeter from the lens. 48 is beyond the board, that's the reason why I put likewise. So in this case, the image is obtained at a distance of 48 centimeter from the lens, and you can see this concave lens has produced a diverging effect, whereas convex lens is producing a converging effect. So first case you got the answer as something like 12 centimeter. Sorry, what we got the answer? 7.5 centimeter. Second case we got the answer as 48 centimeter, and that's all what we are going to study for today. Thank you.